Okay, welcome to video number 6. We're going to be talking yet more about p-values because that's what we're doing in this section. So let's start actually calculating a few p-values. Nothing terribly complicated, but these are going to be some p-values. So quick review, hypothesis tests are about using data which might have come from the null hypothesis or might have come from something other than the null hypothesis, possibly the alternative, to make a reasonable guess about whether the null hypothesis is true or not. Do we reject it as a plausible explanation for the data? Because we can't know if it's really true. All we can say is, well, it's not really believable. Or do we say it is believable? And if we reject it, then we retain the alternative and we say that's more believable. And if we retain the null hypothesis, then we don't go with the alternative. We say the null is still too believable. We can't really invest in this alternative business. So statisticians like precision, and so we calculate a p-value. And so let's look up here. I tweaked this graph a little bit to reflect a little bit more precisely what's going on. P is the probability of this happening. It's the probability that the null hypothesis is true, first of all, and we make this mistake, and the data look so consistent with the alternative hypothesis. The data are sort of deceptive, and then we will end up making a mistake because we will reject the null hypothesis there. So P is the probability of the data looking like the alternative hypothesis when the null hypothesis is actually true, essentially. So going back with exercise, the same one exercise we had in the last video, but with the numbers modified a little to make it easier to calculate. Let's work through some numbers. You do not need to know how to calculate these numbers right now. We'll work a little bit on this in probability. Some of you have a probability background. Some of you are just good at thinking through this stuff. Either way, it might make sense to you, it might not, but I'm hoping you can at least follow the logic process, even if you can't follow the math at this point. You'll definitely be able to follow it later on in the semester, I suspect, but right now it's not important that you follow the math. Just see this is how we get specific p-values. So your friend says he can predict the future. This kid, and this time, let's say you toss a coin 5 times, not 6, and he guesses it each time. What are the null and alternative hypotheses? So if you really want to have some practice with that, pause the video now and write these down, and then see if you got something that's basically the same. Okay, moving on. I chose null hypothesis, he can't predict the future, which would mean that he was just lucky and guessed by chance. I'm not sure I have to write all that stuff down. It's really just that he can't predict the future. The alternative, he can. He can predict the future of coin tosses, which could be useful in some circumstances, I suppose, mainly gambling. So the p-value question, see if you can write down the question that the p-value answers. Moving on. If Fred can't predict the future, so you always have to start with if the null hypothesis is true, and you look up here and say that's that. If he cannot predict the future, if his guesses were just totally random, then what's the probability that we should see this 5 guesses correct out of 5 tries? So can you figure out the p-value? If you have a little background in probability, you might be able to. If you don't, then don't worry about it. This is not important that you be able to figure this out right now. There are lots of ways to figure out p-values, and we'll spend a lot of the semester on this. We're not really starting with that. I just want you to see how it works. So the answer can be figured out with some pretty simple probability. The probability of something like a coin toss, a repeated random event with a known probability for each toss, for that happening a bunch of times a particular way, is the probability of it happening one time that way, multiplied 1 time for each time it might happen. So the probability of guessing 1 coin toss correctly by chance, if you've got nothing, the probability of guessing the coin toss correctly is the same as the probability of it coming up heads or it coming up tails, as it turns out. Guessing a random event with a 0.5 probability is 0.5 probability. So to figure out the probability of guessing 5 times in a row correctly by chance, you have to do 0.5 times 0.5 times 0.5. I used asterisks for multiply. I sometimes use x's. Computer stuff usually likes asterisks, the shift 8 business. So 0.5 times 0.5, so 0.5 to the 5th power, actually. And the result is about 0.03. Those numbers get smaller and smaller, if I did my math right. And always a question. So the p-value is 0.03. This is the probability of this data, or more extreme, but there is no more extreme. I made the situation simple for this. This is the probability of observing our data if the null hypothesis is true. We observed him getting it 5 times in a row. How likely is that if the null hypothesis is true? 0.03. Now, logically, you should be asking yourself, well, how likely is this if the alternative hypothesis is true? We could figure that out if we specified an alternative hypothesis and said, how clairvoyant is he? But we're not going to. Null hypothesis testing is kind of dumb this way. You just don't even talk about the alternative hypothesis. And we'll talk a little bit about that when we talk about power, where we have to specify something. So an interpretation, sort of a report of the results of this research study would be, if Fred can't really predict coin tosses, then there's a 0.03 chance, or a 3% chance, that he could correctly guess 5 coin tosses in a row. That's how we would phrase this p-value as a sentence. So the probability this still could have happened by random accident. Keep that in mind. There's a 3% chance it could have happened by accident, even if he's not clairvoyant. But now we know that it's only 3%. And if you're comfortable with saying 3%, oh my gosh, you're clairvoyant, or saying 3%, no, you're not clairvoyant, I need more evidence. You decide whether that works or not. Would this convince you? That's your decision. And we'll talk a little bit more about that later. Another example, also with gambling, because it works out nicely. Alice wins 4 poker hands in a row, and each time she has a 3 of a kind. 3 jacks, then 3 queens, then 3 nines. She doesn't request any cards from the dealer. She doesn't say, hit me. She doesn't say, I'll take 2, anything like that. She just gets the 3 of a kind and plays it, and she wins. And she says she's just lucky. Is she cheating? What are the hypotheses? Okay, here they are. No, she's not cheating. She's just lucky. And alternative, she is cheating, and the hands were not random. Somehow she cheated. We don't have to know how she cheated, by the way. We can still talk about the probabilities associated with these hypotheses. The p-value question, again, write this out if you really want to test how you're learning stuff here. Moving on. Something like, if she's not cheating, if the cards were dealt randomly, if this was just chance, then what is the probability that she would be dealt this data, 3 of a kind, 4 times in a row? That's actually a lot. So you check online then, and you find the probability of being dealt 3 of a kind is 0.02. Can you figure out the p-value? Okay, going on to the answer here. This is really similar to the previous one. If you know the probability of this happening once, then the probability of it happening repeatedly, if each time is independent of the one before it, is just that multiplied. So 0.02 to the 4th power. Actually, I think I did to the 5th power. I did an extra one there. Anyway, the result is ridiculously improbable. The result is really small. 2 chances in 10 million, 1 in 5 million. This is a very, very small number. So the probability of the data given the null hypothesis is 1.9 times 10 to the negative 7. That's the p-value. It's a very small p-value. So the interpretation, if she's not cheating, there's only about a 1 in 5 million chance that she would be dealt these hands 4 times in a row. So it still might have happened though, right? Life is long, the universe is a big place. It could have happened. That's one of the things randomness means, is that we can never say this could never happen. We just say it's unlikely or it's likely or something like that. So do you think she's cheating? So here's another example. There's something called the guilty knowledge test that you can give if you're a polygraph examiner, a lie detector person. So Lenny Lightfinger, he's given the guilty knowledge test, which means that he's hooked up to the polygraph and he's asked a bunch of multiple choice questions. He doesn't even have to answer them. He just has to think about them and process the information. And then he'll feel some stress if the answer, on the option that is the true answer. So if the interrogator says, how much money was stolen from the cash register? A, $5, B, $5,000, B, $25,000, C, $50,000. And she pauses on each one. If he really knows the answer, then he's probably going to have a spike in his heart rate and his breathing and stuff like this that can be detected by the polygraph on the $25,000 mark, because he knows there was $25,000 in the till, and people react that way in general. It's actually a very cool thing you can do. So she asks him 8 questions, and his autonomic nervous system arousal is the highest for the guilty knowledge option, the true option, on 7 of those 8 questions. So is he guilty? The null hypothesis is that he's innocent. The alternative hypothesis is he's guilty. The null hypothesis is that pattern, because your autonomic nervous system is constantly fluctuating, and one of those numbers is going to be the highest, right? The A, B, the C, or the D is going to be the highest for probably random fluctuation reasons. So the null hypothesis is that the pattern is just random fluctuations, but the alternative hypothesis is that that wasn't random. His pattern is due to guilty knowledge. So what would we expect if he's not guilty? Well, he should show the guilty knowledge pattern on 25% of the questions, on 2 out of 8, because there's a 25% probability of randomly showing the pattern on any one question, so that multiplies out nicely. So on 1/4 of the questions, 2 out of 8, but he actually got 7 out of 8. So if he's not guilty, what's the probability that he would show a guilty knowledge pattern on 7 or 8 questions out of 8? So these questions are all about lying, cheating, misrepresenting, but actually probability theory has a nice long history as far as that goes. So the answer here, we can figure out the probabilities by multiplying the way we did before. The probability of 7 guilty knowledge responses, given that he has no guilty knowledge, is this, 0.25 to the 7th power, so 0.000061. I said right the others. And the probability of 8 responses, given that he has no guilty knowledge, in other words, just by random chance, the probability of basically getting 8 questions right on a multiple choice exam is 0.25 to the 8th power, which is 0.000015. So if you add those two things together, 0.000061 plus 0.000015, that's the probability of 7 or 8. So he got 7, and we have to factor in the possibility it could have been 7 or 8, because we would have accepted the 8, right? If he'd gotten 8, we totally would have gone with that too. So the probability of the data given the null hypothesis is 0.000076, or less than 8 chances in 100,000. So is he guilty? Is that unlikely enough for you? Or do you need it to be an even smaller p-value before you decide that Lenny, that you're going to make the decision that Lenny's guilty? And you're not going to know if he's guilty, right? You're just going to make a decision. You're always playing the odds, and you're always running the risk of making a mistake. So let's talk briefly about those mistakes we might make. When we make a decision in a research study, we specify the null and alternative hypotheses, we calculate p, and then we make a decision about the null hypothesis based on the value of p. If it's really low, we reject the null hypothesis. If it's not low enough, we don't reject the null hypothesis. Now there's this thing called alpha. Alpha is our criterion value. It's our benchmark. And if p is less than that benchmark, then we reject the null hypothesis. And if it's greater, then we fail to reject the null hypothesis. If we reject the null hypothesis, then we'll probably say, this shows support for the alternative hypothesis, even though that's logically a little questionable. But no matter what we do in step 3, no matter which decision we make, we might be making an error, and we will never know if we've made the error or not. Once again, I'm hitting this ambiguity and this uncertainty over and over again, because that's a key part of statistics. So if the null hypothesis is false, then we might make a correct decision or an error, depending on what the data looks like. But if it's true, then we might make that decision or that error also. So a slightly different perspective is this. The null hypothesis, false, true, etc. We could reject or retain the null hypothesis, whether the null hypothesis is false or true. I should probably modify this graph a little bit. And either one of those could be a correct decision or an error. We're just going to make one decision, and no matter which decision we make, it could be a correct decision or it could be an error. This is our world. This is the world that we see. We just see that we made the decision because the data were more consistent with one of the hypotheses versus the other. This is our world. This is what you live as a researcher. Anytime you do a p-value, I would argue this is what you live as a human being, because there are so many things that we don't know the truth of, but we have to make decisions about. So all we know is that we see some data, and we make some judgment of whether it's more consistent with this hypothesis or this hypothesis, and then we make a decision based on whether we think it's more consistent here. And in statistics, we're really specific about specifying these hypotheses and about what the decision is, etc. But no matter which decision we make, it could be correct or it could be a mistake. Now, as I mentioned before, alpha, which we'll talk about in very quick upcoming videos, is the criterion level. It's how small p has to be before we reject the null hypothesis. But it doesn't save us from the problems. The problems of uncertainty will stick around no matter what.